Welcome everyone to Data Wednesdays. Today I'm excited to introduce Mattias Steinrucken, who is an assistant professor in the Department of Ecology and Evolution at the University of Chicago. He develops computational and statistical methods for population genomics analyses to investigate the forces underlying genetic variation. Some of the work they do includes inferring demographic histories, doing admixture disease mapping, and inferring selection strength from ancient DNA or time series genetic data. And with that, I will let you go ahead and take it away.
Awesome. Thank you very much. Thank you for the introduction. Thank you for inviting me to speak here. I'm going to start sharing my screen here. Does it look good? Awesome. Okay, so today I'm going to talk about inferring selection, but not specifically from time series genetic data, just more general, the pattern we observe. So so my talk today is entitled Genetic Hitchhiking in Populations with Variable Size. And this is joint work with my postdoc Eric Friedlander, or he did a lot of this work and I'm presenting about it today. And so this talk kind of has three parts. There's a beginning part that I think should be good for everybody. Then there's a middle part that has a few mathematical details, which I wanted to share because that's some part of the project that I'm excited about. And the end has then some more general stuff that I hope, if you didn't like the mathematical part, at least you will join me for the last part again. Okay, so before I get into genetic hitchhiking in populations with variable size, I just want to introduce the whole thing we're interested in more broadly and just talk about why we're interested in doing this. So in general, we are interested in studying these type of things, and why they relate to this I will get to in a second, because we're interested in adaptation in natural populations or local adaptation in natural populations. And this is a very wide field. A lot of people study this question in different species. And so there's a lot of work on this, and by no means I can give an exhaustive overview here, but I just wanted to mention a few things here that I find in particular interesting in this respect, and that kind of sets the stage. So one paper that I wanted to mention here is this by Seller et al. In 2009, which is entitled Pervasive Natural Selection in the Drosophila Genome, ? So in this paper, they kind of bring together a lot of evidence of the different forms of selection that people have studied in the Drosophila genome to kind of try to come up with a whole picture of what is the evolutionary and especially adaptive forces that shape the genome in Drosophila. Another example, so as I said, there's people studying this in many species and many different methods, but another example that of course I'm more interested in is adaptation in humans, and I put up this picture from this paper by Van et al. In 2016, going global by adapting local recent human adaptations. So in this paper, they also try to give an overview over what people have studied and found in human populations that showed signals of adaptations in this particular perspective to local environments that they encountered in different places around the world. And so there's, again, a lot going on here. Maybe some quick examples I wanted to mention is that, for example, with the cow here, it indicates lactase persistence, which is this variant that is kind of well understood, that there is a variation in a specific gene that causes lactase to be, that people can digest lactase into adulthood. And of course, this conferred an advantage when people started to drink milk. And kind of on the other end of the spectrum, this is where lactase is a specific genetic variant. There's kind of this polygenic selection that also happens in humans, where here height is indicated as such, where you don't have a specific genetic variant that contributes to a trait that is under adaptation, but you have this, you have a lot of genetic variation spread out across the genome that all contributes to this specific trait that is under adaptation, and that also causes some form of selection. One thing I also wanted to mention, just because Emilia is in the audience and has worked on investigating this loci, there's also some signals of high altitude adaptations in different parts of the world. Specifically in Tibet, there's this gene E+1, which is strongly involved in that. So with this, I wanted to show there's different things that adapt in humans in different local environments, and there's different forms of selection that make this happen. And so today's focus, I'm not going to go into all of these different types of selection. I'm going to focus on selective sweeps. And so that brings us to genetic hitchhiking, which is something that is related to selective sweeps. And let me go through this, and then it will kind of become clear why it's called genetic hitchhiking and how it relates to selective sweeps. So the idea behind genetic hitchhiking, which is a term that was coined by Minor, Smith, and Hay in 1973, is that a beneficial allele is introduced in a population at a low frequency, and because it is beneficial, it will increase in frequency, and more individuals will have this allele. So it sweeps to fixation. That's why it's called a selective sweep. Interestingly, it also, while this allele sweeps to fixation, it impacts linked neutral genetic variation. And again, this is a phenomenon that has been known for some time. So there's a lot of overview articles that talk about it, but I just happened to show Kelly and Swanson, 2008, that kind of has this diagram, this cartoon of how genetic hitchhiking works. And this goes as follows. So in this panel A, on the left-hand side, you have just a population with a lot of neutral variation in different parts of the chromosomes. But this is kind of the beginning of the selective sweep, where an adaptive allele arises in one individual on a specific genetic background. Then, because this allele is adaptive, it has a selected advantage. It rises in frequency, so more and more individuals will have this allele. But until ultimately in the panel C, you see that the whole population all have the adaptive allele at this specific locus. However, what you also see is that due to chromosomal linkage, the neutral variation that was present on the one chromosome where the adaptive allele arose gets dragged up to high frequency as well. And that is why this term is called genetic hitchhiking, because the neutral variation that just by chance happened to be on this chromosome hitchhikes with the adaptive allele and also increases in frequency. And this then the other way around causes that a lot of the neutral genetic diversity was present in the population in the beginning is lost from the population. However, as you go along the chromosome further away from the selected locus, recombination will become more and more likely and can cause some of the neutral variation to escape from, to get onto the selected background and thus escape this purging of the population. So in the end, each individual has the adaptive allele, and the genetic background is homogenized a lot, but there is the chance that recombination reestablishes some of the heterogeneity. And so knowing about this effect, that we can think about exactly what this this effect of the linked neutral loci looks like, and how we can study data to find this. And what I mean by this is that the genetic hitchhiking, as I said, it kind of extinguishes neutral diversity around the selected locus, and thus the signature that we can detect in population genetic data of these selective sweeps is reduced genetic diversity around a selected locus. And again, there's a lot of work that about the subject. So I just happened to choose this picture from this paper by Kim and Stefan in 2001. But it shows that the genetic diversity as measured by heterozygosity is lowest around the selective sweep, around where the selected locus is. And as we go further along away from the chromosome, recombination gets more and more likely. So it can restore the genetic diversity. It's more and more likely that it restores it. And so the heterozygosity, as we go away from the selected locus, increases again. And so this is this characteristic pattern of genetic hitchhiking that we can hope to detect in population genetic data to learn about where in the genome selective sweeps happened. And so this detecting the signature, again, what I'm saying is nothing new. People have known about this a long time. And so there's quite a lot of methods that aim to find these specific signatures in population genetic data to learn about selection in the genome. This is a totally non-exhaustive list, but some examples include these sweep finder method or other methods that have finder in the name. And they usually proceed by having a model that tells you how much the diversity is reduced, and then using some likelihood framework to infer where selection happens. There's another class of methods, these extended haplotype heterozygosity or integrated haplotype score methods that more directly aim at identifying these long unbroken tracts of the genome that is this hallmark signature of a selective sweep, and go about studying selective sweeps this way. And then some other methods, and I wanted to mention this in particular because it comes out of Suhini's group, is this method SWIFR that takes another approach by basically taking a machine learning approach where you train your classifier on some summary statistic of data that is generated under a selective sweep, simulated under a selective sweep, and then you apply it to your genomic data to identify these selective sweeps. I hope I didn't mess up this explanation in a nutshell. So there are a lot of methods that search for these characteristic pattern of these selective sweeps. But there are some drawbacks to some of those, and that's why I'm still interested in developing further methodology here. A lot of these methods can tell you something about significance. So they find these reduction in genetic diversity and tell you, okay, there was a selective sweep here, but not a lot of methods actually allow you to further dig into it and say, okay, to characterize the selective sweep more in terms of when it happened, how it happened, what was the strength of selection. And so I'm kind of interested in using these patterns as well to do some more inference about the parameter underlying the population genetic model. Not all of them can account for variable population size, and this is especially interesting when you detect selection, because changes in population size can result in some signatures that kind of look like selective sweeps, and so you have to kind of account for that correctly if you want to identify selective sweeps. And another thing a lot of these methods do is that they can kind of detect very strong positive selection, but one could also be interested in finding maybe some weaker signals if one can find those, or different forms of selection that is not positive selection, but maybe even balancing or something like that. So as I said, a lot of these methods work pretty good in their respective domain, but I think there are some things that one can still investigate. So with that being said, the overall goal, and I'm today presenting some steps along the way, is to develop a framework to characterize the dynamics of genetic variation under selection and the impact of this dynamic on the dynamic of linked neutral variation. And I want to do so by explicitly modeling the population genetic processes that happen in the population. Want to have be able to accommodate some very general selection model. I have to account for recombination explicitly. And as I said, I also want to be able to incorporate variable population size into the model. And so in order to do this, in order to develop this framework, I'm going to use the methods that has been used in different contexts before and successfully in those contexts. And that's why I think it has a lot to bring to the table in this specific scenario, which is this numerical framework that has been termed the method of moments by some people. And it is a framework to efficiently compute likelihoods and statistics in population genetic models. So essentially describe the genetic variation under specific population genetic models. This framework has been used for single locus statistic like the site frequency spectrum by Evans et al. And Juganos et al. For demographic inference, more and more complex demographic models. And it also has been applied to true locus statistics like linkage disequilibrium and the likes to infer demographic history by Rexdale and Gravel and by Kam et al. To infer recombination rates. So that's what I mean. This framework has been applied in these respective domains successfully. So that's why I think it has something to offer in terms of studying genetic variation under selection. And so before I get into the full general model that we actually developed and that we need to understand this type of scenario. I'm going to introduce the method kind of in a single locus example to hopefully make it a bit more accessible. So here's kind of what the model that we use is, and then how we have to think about this. The model we use is the Wright-Fisher diffusion, which is a model that is used in population genetics to model a randomly mating population of 2 haploid individuals. So you have a population of a bunch of individuals of a certain size, and this is randomly mating. And in this simple example, we just consider a genetic locus, a single genetic locus with 2 alleles, small a and capital A. And we just track the frequency of capital A alleles in this population as it evolves through time. And we denote it by yt. So we say yt is the frequency of the A allele at a given time t. We initialize the A alleles at a certain frequency. So we say y0 is a certain frequency, and then we go forward in time, and this population evolves forward in time through generation by generation. And since it's a randomly mating population, these allele frequencies will fluctuate at random. Sometimes they will go up, sometimes they will go down. So it's a random quantity, this yt. Just a quick note, time t is measured in generations. So it's this population rescale time where t equal to 1 corresponds to a step of t equal to 1 corresponds to a step of 2 generations. It's not very important. I'm just wanted to add it here for completeness. But yeah, so it's think of time as generation pass. So as I said, if I start with a certain proportion of A alleles in the beginning, this across over generations, this allele frequency changes at random. So if I want to know its distribution of a certain time, it's a random quantity. So I have to somehow describe how is it distributed at a certain point in time. And in order to do that, what people use to describe this distribution is the so-called transition density function, PTXY, which is a probabilistic density in Y. It basically tells you the likelihood that if you initialize your population at frequency X and you wait for a certain time T, what is the likelihood that you find your allele at a certain frequency? And so it's a probability distribution in this variable Y, in this frequency. This quantity satisfies, or the way people describe this transition density function on a more abstract level is that it satisfied a certain partial differential equation, which is given by this left-hand side is the derivative with respect to time. On the right-hand side, we have this operator that is applied to the transition density function, which is sometimes called a generator as well. And just I hope some people are familiar with this. If you have a scenario that I'm just talking about, the single locus with just 2 possible alleles and only genetic drift is acting, then this very classical form of this generator for the Wright-Fisher diffusion has this form 1/2 x times 1 minus x times the second derivative of the transition density. So I hope some of you might have encountered this in an introductory population genetics course. So the details of this are actually not very important. The important thing is we can define this transition density that tells us the random distribution of the allele frequency at a certain time t in the future. And we can describe this by introducing this partial differential equation. So this transition density could in principle be obtained as the solution of this partial differential equation. But that is sometimes a bit tricky to obtain. So we actually want to go some different route to get at quantities that we're interested in. And so what are the quantities that we're interested in? We're not necessarily interested in the population allele frequency at a certain time because we might not even be able to measure the population allele frequency. But what we can measure is we can take a sample from the population and ask what is the probability to observe a certain number of capital A allele in that sample. And this is exactly what the sampling probabilities or the allele frequency spectrum tell us. So what we do here is we wait until we let the population evolve until time t, and then we take a sample of n haploid individuals, and we want to know what is the probability that we observe I individuals that have a capital A allele under our model. And we denote this probability by MNIT. So the way to compute this probability, one way to compute this probability is shown in this equation, where we say, okay, this probability of obtaining I capital A alleles in a sample of n individuals is given as follows. If the population allele frequency at time t would be y, then this probability would just be binomial sampling with success probability y. However, and this is captured by this sampling polynomial here. However, we know that the distribution of allele frequency at time t is a random quantity. So in order to get this probability, we have to integrate this binomial sampling probability over the transition density function that tells us how likely are different frequencies at this time t. And so one way to get at these probabilities would be to compute the transition density, solve the PDE, the partial differential equation, and then numerically integrate this integral. However, that's cumbersome and error prone. So but we are in luck because there's a different approach to this. And this approach is basically, not going to go too much into detail, but it's based on Dinkins formula that tells you that these sampling probabilities satisfy certain ordinary differential equations. And you can derive them by using the specific form of this generator from the Wright-Fisher diffusion. And the reason why this is good is that ordinary differential equations are much more stable and much easier to solve than partial differential equations. So without going too much into the detail, what we have now is that we can compute the sampling probability as the solution of a certain system of differential equations. And if we want to write down the system, we can kind of write it down like this. So each sampling probability solves an ordinary differential equation. So we can put them all together in the system of differential equations, where we say, okay, if we take a sample of size n, we can see 0 A alleles in the sample, we can see 1 A allele in the sample, we can see 2 A allele in the sample, or we can see n A alleles in the sample. So each of these events has some probability, and they are given by mn0, mn1, and so on. So if we think about all these probabilities, each of them satisfies a differential equation, and so we can put them all together into one vector and call that vector capital M, or boldface capital M, and say, okay, that this vector of probabilities, of these sampling probabilities, satisfy a certain system of differential equations, which is given by multiplying this vector M with a certain matrix Q, and this Q in this specific case represents the genetic drift in this system. I'm not going to go into the details of exactly how what Q is, but using this whole procedure, we can derive Q from in this scenario and write this system down. And then the approach to compute the sampling probabilities, the probability of sampling a certain configuration at time t, is to initialize this, this differential equation with the respective values at time 0, which you can get from the initial condition, and then just use some numerical, numerical scheme to solve these differential equations forward in time until we hit the time t, and then we have our sampling probabilities. And it turns out that this system is very amenable to numerical solutions, so it's very stable and can give us these probabilities very efficiently. So this is kind of in a nutshell how this numerical procedure is set up in this simple single locus example, where we have looked at a single locus with 2 alleles. However, if we are interested in understanding the hitchhiking effect, where we have one locus where selection is acting, and we want to understand what is the impact of this on linked neutral genetic variation, this model is not sufficient. We have to kind of extend our model to a 2 locus model, where now we have a locus where we have 2 alleles A and B, and we just arbitrarily say capital A is the one with the beneficial allele, the one with the selective advantage. And then we have a second locus with 2 possible alleles, small b and capital B, that is a certain recombination distance away. And so we want to understand in a population model where we consider this 2 locus model, how does the selection influence the genetic variation of the linked allele. And just for completeness, the relative fitness coefficients, I denote this by sigma. That will kind of show up a bit later again, where sigma is 2NES, and S is the per generation selective advantage that the A allele confers. So now we want to understand how the genetic variation at these two loci evolves forward in time under a model where selection is acting and recombination as well. So now we have to consider a more general genetic type. Now we don't only have a single locus with two possible alleles where one frequency can tell us everything about the state of the population. Now we have, in this two locus model, 4 possible haplotypes. An individual can have the haplotype small a, big B, and all the other ones. So we have 4 possible haplotypes. And each of these haplotypes can be at a certain frequency in the population. So to describe the population, now this X is a vector of 4 numbers, where each number says what proportion of the population has a certain haplotype. But once we take this perspective and represent the state of the population by this collection of frequencies, we can then actually do the same thing again. We can again use this Wright-Fisher diffusion framework to say, okay, this again, we can define a transition density function in this Wright-Fisher diffusion where we say the density PTXY now tells us if we initialize the population with these haplotype frequencies and we wait a certain amount of time t, what is the likelihood to observe certain other haplotype frequency y, or what is the distribution in the haplotype frequencies? How likely is it that we observe certain haplotype frequency at a later time? The whole system now becomes a bit more complicated, but we can still derive this partial differential equation that this transition density is a solution of. But now this operator, this generator on the right-hand side of the partial differential equation is a bit more complicated. There's more forces acting. So now we have genetic drift acting, mutation acting, recombination acting, and selection acting. So recombination, because recombination can happen between our two loci as we move forward in time, and selection happens at this one locus where we have a beneficial allele. And so it turns out that you can write this generator in this form. And I'm not going to go further into the details, but just that is kind of the sum of these different forces that act on the genetic variation in the population. And then we can do the same thing that I went over in a bit more detail in the single locus case. Again, we can say, okay, now we want to compute the probability of observing a certain configuration of haplotypes at a given time t. So we let our population evolve for some time t, and then we draw a sample of a certain size n, and we ask, what's the probability that out of this sample we see a certain number n small b of small b haplotypes, a certain number of n small a capital B haplotypes, and so on. So we draw a sample from the population, and we now look at the genetic variation of these two loci at the 4 possible haplotypes, and we ask what's the probability that we see a certain number of haplotypes in our sample configuration. And again, I can put all of these probabilities into this vector boldface M. So the boldface Mn is now the collection of probabilities of all configurations of size n. What I mean by this is that if you take a sample of size n, you can observe different numbers of AB alleles. So you can observe more or less of the small a, small b haplotype. And correspondingly, in the sample, you would then observe more or less of the other haplotypes. So by that, I mean just if I take a sample of size n, there's different combination, there's different configurations of haplotypes that I can observe in a sample of size n. And I'm interested in computing the probabilities for all of them. And that's why I put them together in this vector boldface M. Very similar to before, I now have again, can derive a certain set of system of ordinary differential equation that these probabilities are the solution of, where in this differential equation, I have again a term that, that captures the genetic drift in the model. I have a term that captures the mutation in the model. I have a term that captures recombination in the model. and I have a term that captures selection in the model. And each of these terms are a certain matrix times these probabilities. So in principle, I have now derived this system of differential equations that is satisfied by these probabilities of the sample configuration. I could obtain these probabilities at a certain time t by solving the system of differential equations. However, there's two things to note before I can really do this. One thing to note is that the drift is now time dependent. And what that allows me to do is that I can increase and decrease the intensity of genetic drift at certain points in time. And what that allows me to capture is that some basic population genetics tells you that in large population, genetic drift is small, whereas in smaller populations, genetic drift is stronger. So this time varying genetic drift allows me to actually capture population size changes. So if I am interested in a certain population size history, I can mirror this by changing the genetic drift accordingly and having genetic drift be stronger in small populations and weaker in larger populations. So this time dependency in the genetic drift term allows me to capture the fluctuating population size. Another thing to note is that this system is not closed, what people call closed. And that is because these terms, the recombination and the selection term, depend on mn+1. So in order to compute the sampling probabilities of a sample of size n, this tells me I have to know the sampling probabilities of a sample of size n+1. But that would in turn mean if I want to know the sampling probabilities for n+1, I would need the sampling probabilities for n+2. And for n+2, I would need n+3. And so it's easy to see that this doesn't give you a point to start. This is what people refer to with not closed. There's no point where I can start the system because whenever I want to compute something, that depends on something that I haven't computed already. So upfront, this kind of prevents us from solving this system of differential equations. However, there's a solution to this problem. And in order to solve this problem, I can say, okay, but let's then just estimate the sampling probabilities for a sample of size n+1 from the sampling probabilities of a sample of size n. So let's kind of take what we know about the sample of size n and kind of extrapolate in terms of what we think our best guess would be for these sampling probabilities for a larger sample. And the way we do this in a nutshell is I have shown you this kind of graphical depiction of how this works in a single locus scenario, but we can extend this to this more complicated two locus scenario. In a single locus scenario, this plot depicts the sampling probabilities of observing a certain number or frequency of A alleles in a sample of a certain size. And the assumption here is that the population is at stationarity. So at this, under the stationarity assumption, we can compute the sampling probability exactly and can plot this in this plot. And the reason why I plot the frequency of the A allele on the x-axis and not the number is because if I plot the frequency, they all can have the same x-axis. So if I plot these probabilities, I see, okay, I see a bunch of curves. Actually, those are discrete values. The lines between them are just a plotting device. And they have a similar shape, but apart from that, they don't have too much more in common. However, it turns out that I can rescale them and make them lie exactly on top of each other. And it turns out that the rescaling here is just the sample size. So effectively, the probabilities of a certain order, the sampling probabilities of a sample of a certain size, properly rescaled, converge to each other and can be used as very good approximations to each other. So then the way to get at my problem of estimating probabilities in a sample of a larger size from the probabilities of a sample of a smaller size, I just rescale the probabilities for the small sample, interpolate them to approximate the ones in the large sample, take back the rescaling, and then I have a highly accurate approximation of these sampling probabilities, which I hope this plot convinces you to some degree that this works, but it can be shown to work in the more complex model as well. And just a small tidbit, we use the logit for stability, but that's not important. So the important thing is that we can use the sampling probabilities for samples of size n to approximate the sampling probabilities for larger samples using some numerical procedure. And this is kind of related to the more general questions of if I have a sample of a certain size, what do I expect from a larger sample? So if you kind of consider populations and you sample from them, you often, or sometimes you want to know, is there any benefit from drawing additional samples? And so some procedures like this and similar ones that have been developed can help you to understand what more would be to gain from if I draw a larger sample. So this is a kind of more general problem. But the specific use we get out of this in this setting is that we can use this to close this equation, because now we can say, okay, we need for the differential equation for mn, we need mn plus 1, but we can approximate this from mn. So ultimately, we only need mn. And the same goes here. Here we need mn plus 2, but we can approximate this from n to n plus 1 to n plus 2. So ultimately, we also only need mn. So in essence, to get an approximation to the right-hand side of this differential equation, we also only need mn, and thus we can plug in this approximation and solve this system. And so this is exactly how we get numerical solutions in this more complex two-locus system where recombination and selection is acting. The procedure is we use the approximation to close the system of equations, and then we solve the system numerically using some standard numerical ODE solving scheme. And what this brings to us is this can be used to compute these sampling probabilities, the probabilities of observing certain sampling certain genetic variation at certain points in time in the future, but it can also be used to compute expected values of certain statistics of the population that we might be interested in. And so this is kind of where the math part ends and where we get back to maybe some more interesting pictures. So now in order to, on the one hand, assess how accurate our numerical solution of this dynamics is, we're comparing the numerical solution to simulations under population genetic model. And as I said, to on the one hand show the accuracy of our method, but on the other hand also maybe exhibit some interesting features that the genetic variation in this scenario, that the genetic variation exhibits in the scenario of selection action at one locus and how it impacts a linked neutral site. So let's start out maybe, before we start out, one thing that I had in the title and that I wanted to stress here again is that, as I said, our numerical solution allows us to model a changing population size history. So it allows us to model, have fluctuation in the population size. And so in this simulation, particularly, we use this to account for a cartoon model of a European demographic history, where we say, okay, some time ago in the past, or for some time, we had a stable population size at size 10,000. Then 4,000 generations ago, this dropped to a size of 2,000. And then 1,000 generations ago, exponential growth started to bring this population size up again and increase beyond what it was before. And so this is kind of modeled after some parameters that people have inferred for European demographic history. It's not the exact parameters, it's a cartoon, but it's very much inspired by some parameters that people have inferred from real data. So what I wanted to say is our method allows us to have changing population size. And so in these simulations and these comparisons, we use that to simulate under this changing population size model, and also to see whether our numerical approximation can capture what happens in the simulations. And one last thing to note is that there are these arrows here. So we also considered introducing the selected allele at the low frequencies at different points in time. So at some point, we eta 1 is we introduce it way back in the past. Eta 2 is we introduce the selected allele at the time of the when the bottleneck starts. And eta 3 is we introduce the selected allele just before the exponential growth starts. And we want to see whether there's some interesting dynamic and whether our numerical procedure can capture those. So having said this, let's just start with a very simple perspective. Just look at the expected frequency of the beneficial allele. So our model numerical procedure allows us to compute the expected frequency of the beneficial allele, which is a very easy special case of the model. And so in this scenario, we, again, as I said, we introduce the beneficial allele at these different points in time at a certain initial frequency with a selection coefficient of 10. 2NES is equal to 10 in this plot, or 2NES is equal to 100 in this plot. And what we see is we see our ODE in these and the subsequent plots I will plot as a solid line. The simulations I will show as a, the mean of the simulations I will show as a dashed line, where the highlighted area kind of gives a confidence bound around these. We see that indeed the selected allele, because it's selected, goes up from its initial frequency over time. If the selection, if 2NES is equal to 10, it kind of just rises gradually and is, goes up, but not very fast. However, if the selection is stronger, it goes up very quickly. And this is kind of regardless of when it is reduced. If it's selected for, it always goes up very quickly. And comparing the simulations with our ODE, we see that our ODE is pretty good in actually capturing somewhat of the dynamic that happens in this model. So that's kind of just looking at the frequency, expected frequency of the beneficial allele. But since we did all this effort to look into how selection at a selection for a beneficial allele at a certain locus impacts neutral genetic variation at a linked locus, we also want to look into some things that describe this scenario with linkage more closely. So especially we can look at the expected linkage disequilibrium between the selected and the neutral locus. And in order to kind of have something to begin with, we have that linkage disequilibrium is not zero at the beginning. We couple initially the beneficial allele fully with one of the neutral alleles, so that initially we do have some linkage disequilibrium in the population. And rho in this set of simulations is pretty small, so they are very tightly linked, so it's kind of two loci that are very close together. And what we see now is that something more interesting happening. Let me maybe start with the large selection coefficient. We see as expected, so people kind of knew that already, but linkage disequilibrium goes up. So as the frequency of the beneficial allele increases, it first increases linkage disequilibrium, but then once the beneficial allele goes towards fixation, it then again decreases linkage disequilibrium. And so the simulations show that, and our numerical model captures that very accurately, that in the strong selection case, linkage disequilibrium goes up quickly and then goes down quickly again. And I guess with this green line, which is introducing it here, it just didn't have a chance to go down yet. But we also see that the top is kind of influenced by where the population size is at. And if we have slightly smaller selection, something more interesting happened, because kind of the increase in linkage disequilibrium is not quite at the top yet, or it just hits about the top when the bottleneck is hit. But then once the bottleneck hit, it just decreases very rapidly. So again, I guess one could spend a lot of time to figure out what exactly the underlying mechanisms are there. But just what I wanted to point out again is that no matter what the underlying mechanism is, it is captured in the simulations, which is kind of the ground truth. But our numerical procedure also captures these type of effects pretty accurately. So this is kind of just looking at some statistics, some simple statistics like expected allele frequency and linkage disequilibrium, to just convince ourselves that we're doing well when we compare to simulations. So let me get kind of into a bit more looking directly at what I had shown initially and what I kind of used as a motivation for the whole talk, that is genetic hitchhiking. What is the reduction in genetic diversity around a selected locus? And to look at that, again, we can use our numerical procedure to look at that in particular. We can also simulate it. So again, we see comparison of simulations and our numerical procedure. And what we plot here is as follows. We kind of look at the genome. So on the x-axis is now kind of the genome dimension where it's 0. That's where the focal locus, the selected allele, is. And as we go away from this focal locus, we look at loci with increasing recombination distance from the focal locus. And on the x-axis, we have the expected heterozygosity, like a measure of genetic diversity. And just quickly, in this case, we only look at the simulations. I'm only showing the simulations here where we introduce the selected allele way in the past. And so, yeah, as I said, we have the selected allele is introduced at eta1, and then we can follow this heterozygosity along the chromosome through time. We can look at it 10,000 generations before present, 7,000 generations. So we can look at time slices of this heterozygosity along the chromosome and as it evolves due to the selection. And we do see this reduction in heterozygosity due to the selective sweep that is happening here. And we do see it in sweeps with different strengths of selection. But there's also something interesting to say about the temporal dynamic and the total decrease that we observe, which kind of depends on the selection coefficient. So what we see here is that initially, just when the selected allele is introduced, so basically in the neutral background, heterozygosity is just at a background level everywhere, because we initialized it that way, that we have, say, we have a background heterozygosity. Then as time proceeds and the selective sweep starts, the selected allele starts to increase in frequency, we see that the heterozygosity dips at the selected locus, and it dips more and more. And then an interesting thing happens again if we hit the bottleneck. A bottleneck usually, once the population goes through a bottleneck, the bottleneck decreases the genetic diversity at an overall level. So the overall genetic diversity is decreased during the bottleneck. So what we observe from the bottleneck is that the total amount of heterozygosity is decreased. And that is caused by the bottleneck. But we still see some kind of dip that is left over from the signal that we had of selection before. And then, as we go forward, this dip slowly starts to go out as the heterozygosity starts to reestablish itself. And again, this, on the one hand, as I said, this exhibits some interesting features of how this heterozygosity changes over time, but it also, in comparison with simulations, just shows us that what we get from our numerical solution is just the same what we get from the simulation. So we do trust our numerical solution that they do indeed capture the effects of genetic hitchhiking. And another perspective on this that maybe I'm just going to go briefly over is we can also extend this a bit more and look at a folded site frequency spectrum in a window around the selected site. So not just level of heterozygosity, but actually probabilities of observing a certain number of minor alleles. We do this by defining a window, in this case, 100 kb around the selected site, and we just count the number of minor alleles at all the segregating sites within this window. And then we, in the simulations, we simulate the data and count the number of minor alleles. From the numerical solution, we just extract the probabilities of observing this certain number of minor alleles in this window. And we again see some interesting dynamic, which here I've shown you a sigma of 1, which is very close to just neutrality, and a sigma of 50, which is some stronger selection. And what we see is that under this case that is very close to neutrality, as long as the population size stays constant, this site frequency spectrum basically doesn't change, and it's just the same. So it's kind of the neutral expectation. However, once we go through the bottleneck, we again see this general decrease in genetic diversity across all ranges of the site frequency spectrum. So just the line shifts down. And interestingly, once the exponential growth starts, we see this increase in the rare allele classes, which is a hallmark signature of exponential increase. So again, we don't even see the simulation versus the numerical here because they're on top of each other. Our method very well captures what the expected behavior of the side frequency spectrum in this scenario. And then if we introduce selection at an allele in the middle of this window, we see that this again has an impact. This actually has an impact on the side frequency spectrum that we observe in that window, namely selection over time pushes out the intermediate frequency alleles and pushes all the alleles somewhat into the rare frequency classes. And again, this effect is a true effect because it's captured by the simulations and our numerical procedure. Yeah, so all in all, this is kind of what I wanted to leave it with the simulation. I hope I have convinced you that we have introduced this numerical framework, and even if you didn't follow all of the mathematical details, I hope that some of these simulations have shown you that this is indeed a framework that can capture the effect that that a selected allele has on linked neutral genetic variation. And it does so, I didn't say this before, orders of magnitude faster than we can run the simulations. And so maybe I want to close with quickly with some future direction that we want to take this project in. So what I've shown you so far is that this framework is very helpful in studying what type of signature I would expect in certain statistics or certain sampling probabilities under models where hitchhiking is acting, and incorporating the respective population size history. However, what we also really want to do is we want to turn this around and not only study what the genetic diversity that we observe and make predictions, but we want to actually apply this to population genetic data to infer where selection is acting and hopefully infer something about what type of selection or how strong it is acting. And to do that, what we are planning to do is to say, okay, we have this numerical framework that allows us to compute the probabilities of sampling configurations of these pairs of loci in a two locus model. The problem is if we have multi-locus genetic data, that's not two loci, that's multi-loci, just by definition. But in order to apply these probabilities, these likelihoods that we can compute in the two locus model, we can just extract all pairwise configurations from this multi-locus sequence data, compute the likelihoods for all of these pairs, and then multiply them together to get some composite likelihood. And the reason why I think this is a decent idea is that a similar approach has been used to infer recombination rates and has been very successful in that respect. So I think these pairwise composite likelihoods are very promising. However, we wouldn't necessarily compute all pairs. We would just pair each neutral locus with the selected locus and compute the probabilities for all of these pairs and then multiply all of them together. And then we would get a composite likelihood that would allow us to do some parametric inference. Or at first, you might ask, okay, but I don't know the selected locus, so I can't really pair every neutral one with the selected locus because I don't know it. But then I would say we can use this framework, just shift it along the genome to find the selected locus via some likelihood ratio test that would, if you put it at the right place, tell you significantly that there is some selection going on there. But once you use it to detect the signature of selection, you can also then further use the likelihood model to actually perform likelihood, or this composite likelihood model to perform likelihood inference of the parameters of the underlying model, like the selection, the strength of selection, the time of onset of the selection, and things like that. So we are not only trying to find these characteristic pattern of selective sweep and this genetic hitchhiking, but we're also trying to maybe infer based on how exactly the pattern looks, what type of selection was happening. So some preliminary results, we tried some preliminary results using this model, but we encountered some obstacle, which was when we multiplied just all of these pairs together, we noticed that the frequency of the selected allele drives the likelihood of inference very strongly. And the reason for that is that if you observe a high frequency allele at the selected locus, the model says that it's most likely selection because if you start from a low frequency to get to a high frequency, selection is very likely to do so. However, neutral alleles can also reach high frequency, so that caused us a lot of false positives. If we would just try to see, look at a neutral allele, and that happens to be at high frequency, our model would always say selection, although we didn't simulate it under selection. So we got a lot of false positives. And so that's kind of where we are at the moment, but some ideas that we have to circumvent this is we want to somehow tell our model, ignore the frequency of the selected allele and only use the neutral diversity around it, so that the inference is less strongly driven by the selected allele, the frequency of the selected allele. And two ideas we want to follow up here is we can either condition on the selected allele in the sample and make it ignore it that way by conditioning, or actually just marginalizing and just not looking at it at all. And that's actually kind of very similar to the side frequency spectrum pictures that I've shown you before. So anyway, that's kind of where it stands. We haven't really solved this yet, but this is kind of where we want to take this project, to use these numerical solutions to actually do some likelihood-based inference of the parameters of the underlying population genetic model. So with this, I kind of want to end today. Again, I've introduced to you this numerical method to compute statistics and likelihoods in these population genetic models, where we have a look at neutral variation and how it behaves when it's linked to a locus where selection is happening. And I didn't, and this method, I mentioned it, is actually orders of magnitude faster than studying similar things with population. So it's very accurate and very efficient. And as I said, in terms of next steps, we want to implement this composite likelihood framework for inference and analyze data sets, first starting with public data sets to characterize singular selections and to see whether we can actually do this. And another interesting direction I think this model can take that I'm very excited about is that this framework, although I focused on these selective sweeps today, in principle, there's nothing that prohibits you from modeling more general forms of selection, like balancing selection, background selection, or other forms of selection. So I'm also very excited to see whether we can leverage these signals that are caused by at neutral loci by linked selection of other forms, whether we can explore and exploit these signals to learn something about the parameters underlying the model. And lastly, I mentioned very way in the beginning that some traits, especially in humans, are under polygenic adaptation, where there's not a single locus where selection is happening, but more subtle signals at a lot of loci that go towards the same trait. And I'm also very excited because I think putting this numerical procedure in the right framework also can allow you to learn something about these types of adaptation. So with this, I want to thank you all for your attention. Thanks for listening, and I'm happy to take any questions. Thanks.
Well, thanks so much for sharing your work with us. Does anyone have any questions for Dr. Steinrucken?
I have a question. So you inferred you showed us, I guess you said that the selected allele impacts the inference. When you were doing the inference, were you inferring whether there was selection, or were you also inferring the parameters of selection? And would you also be able to infer, I guess you could potentially also infer the population size changes?
Yes, so I think we were actually kind of looking first in just trying to infer the parameter of selection. So we wanted to see whether we can do that before we really get into detecting where selection is. So we focused first at inferring just the parameter for selection. But that's where we noticed that if you have neutral alleles that happen to be at high frequency, then this just tells you there's a large selection coefficient. And since we knew that was not real in the simulations, we knew that this wouldn't work. And so that's why we currently at wondering whether we can use some of these approaches to kind of make the method ignore the frequency at the selected site and just look at the neutral variation around it. Which actually, I didn't know this when we started on this project, but other tests of selections effectively actually do that. So it's kind of a thing we should have done to begin with. we just didn't think about it. And yes, in principle, we could use this, this framework also to infer population size history. I would say that our implementation is a bit more aimed at this whole selection inference, but there's other implementations. For example, this method by Kam et al. That I mentioned at the beginning, which I think would be more amenable to infer population size history. But yes, in principle, you could use these types of models and likelihoods to also do that inference.
It's really cool. Thank you.
I think we have time for one more question if there is one.
I have another question. So you said that it's a lot fast, orders of magnitude faster. How, I guess I'm trying to think of like, you know, like when you do simulations, you do, you select like the size of the region. So in this case, like this gives you the expected, these probabilities of like, I guess the pairwise comparisons. So I guess in this case, when how many SNPs do you have? I guess I'm trying to think of.
So maybe one thing to say about the orders of magnitude is I can't say exact numbers, but the thing there is also that if you want to get these numbers that we compute numerically via simulations, you can just estimate them from simulations, and thus your estimate will be better the more simulations you do. And so it's kind of, you can't make really a precise comparison because you can get vague estimates very quickly from simulations, but if you like kind of want to really precise estimates, you have to run a lot of simulations. So that's kind of why I guess calling it order of magnitude is maybe a bit too hand wavy, but just you can get precise numbers from just doing this numerical procedure, versus if you want to have those numbers from simulation with high precision, you would have to do a lot of simulations. And so that's why I'm saying like this is a good approach to get at these numbers, and I think better than simulations. The other thing in terms of sites, so I think this particular simulation have 100 KB windows. So I mean this is the number of sites basically.
Mm-hmm.
So if we would integrate this quickly, we would know how many there are. But yeah, so I think I don't have the number quite ready, but I would say it's probably on the order of 100. So if this is like 10-ish, then you have like a few left in the other classes. So it's maybe between 50 and 100 probably in this particular setup. But we also use like different window sizes, and then you have more or less segregating sites. But the interesting thing as well is that I mean, the biggest window would be whole genome, but then you don't see any effect of a single selected locus in the middle. So it's interesting to see, and I didn't present this here, but we have some plots in the manuscript that's supposed to be posted to bioRxiv in a few weeks, that show that when you increase the window size, so making the window too small, it gets very noisy, but making it too large, you lose your signal of selection. So there's kind of this ideal window size, which I think is in other studies has also been realized that there's kind of an ideal window size when you look for footprints of selective sweeps. I hope that answers your question to some degree, maybe.
Yep, it does. Thank you so much.
Well, thank you again for sharing your exciting research with us, and thank you everyone else for coming, and we'll see you next time.
Awesome. Thank you very much for having me. Thanks for listening.